So very good morning and welcome to day 4 for this GAN course on combustion theory and applications. So till previous lectures we have emphasized the concepts of combustion modeling and how chemical kinetics concepts were brought into picture, how to frame the governing equations, what are the different combustion parameters that needs attention while modeling. Uh, Here I'll start some basics of laminar premixed flame. In fact, my other colleagues, Professor Marcus also, he will be talking similar concepts. But however, although theories are same, but his way of looking at the things may be different with research point of view. But as far as the course is concerned, we are going through the theory part. So in this lecture, the main intention would be I'll touch upon the first basic phenomena of combustions, which starts with formation of flame, its propagation. We'll try to see, and first simple type of flame is laminar premixed flame. This is something similar to the fact that when you have spark ignition engines where fuel and air mixture is burned together, and we call this as a homogeneous mixture. When you ignite it through a spark plug, it uh, it it creates a flame. Flame is nothing but a surface that essentially distinguishes the region between uh, between the charge and the combustion products. And in the combustion medium, the flame propagates or moves. When it moves, because of the increase in the pressure and temperature of uh, uh, during combustion, it also subsequently moves to ignite the fresh charge. This is essentially required that we need to develop we need to develop some kind of phenomena or mathematical models concepts uh, during the time of combustions. You can see this such type of events only uh, last for few milliseconds, and that few milliseconds it initiates with a flame, subsequently burning all the fuels and uh, and letting the combustion products uh, out, which means that we are looking at the domain of that test window in which flame is generated, it moves, and finally its main intention is to ignite all combustion products. Initial ignition was given uh, uh, manually into the charge, but subsequent ignition happens due to this flame motion. Because of these reasons, because we need to have a sustained flame, the flame has to remain, flame has to be there in that domain till all the fuel air mixture burns completely. Then only we can have a effective meaning of combustions. But however, to have a sustained flame, we also expect that we should create some favorable conditions for that sustained flame. So that's the reason we need to discuss about different factors that influences the flame velocity. And over the period of time, people have done lot of experiments, and among variety of parameters has been studied, and they are simplified by certain correlations, and we call them as a laminar flame-Pritz correlations, which more or less is agreeable to all kinds of combustion uh, involving premixed charge. As a case study, I'll try to see that how that concept is normally extended for homogeneous mixture combustion in a spark ignition engines. As far as these two parts is concerned, wherever we encounter IC engine cores, we normally start with homogeneous mixture combustion, and subsequently how that combustion effects gives rise to variety of phenomena, if it is whether it's a unwanted combustions or it is a favorable combustions, and that is mainly because the kind of laminar flame that we can generate, and uh, subsequently we need to evaluate that effect if at all that laminar concepts was not favored, then what are the effects that we are going to see if the combustion is not complete. So this is the overall things concepts about this lecture today. So when you talk about modes of combustions, we normally think about two things. Uh, one is flame mode. In the flame mode, we have a spark plug, uh, and through this spark plug, the flame gets initiated, and in this zone, all the phase charge gets burnt. Then subsequently the flame moves in the directions of unburnt fuel air mixture, and slowly killing all this unburnt charge into combustion products. So ideally, if this is the domain of domain that flame has to move and propagate, then which means that starting from initiation of the flame, it has to go, and by the time we initiate the flame and it reaches here, all the combustion products has to be burnt. Uh, this is how we do a flame mode combustions. In other things, where you talk about non-flame mode, either in the non-flame mode, normally instead of spark plug, we use fuel injector, and this fuel injector, what it does is that there are possibilities that you can inject this fuel at various locations, and through this we can auto ignite this charge. The auto ignite charge means air and fuel come separately, and they are already in this when the fuel sees that high temperature pressure air, then it self ignites. Although there are flames, there are multiple number of flames that opens up simultaneously, but we cannot actually create a specific flame that ignites the fresh charge. So that is actually, we call this as a non-flame mode combustion. So whatever may be the situations, in this laminar premixed case, we will mostly concentrate on a propagating flame which is initiated by a premixed charge. Many times in engine point of view, if the charges are not ignited completely, it creates an effect which is called as a knock. This knock is a undesirable situation that we encounter in the cylinder of an IC engine, and that is quantified in terms of rapid pressure rise, and it leads to undesirable sound of the engine. So we'll talk about these things, how this knock will form in subsequent slides. The kind of other mode of combustion that we call in this situation where we use this fuel injector, in which we have a non-flame mode situation. Such things we call them as a diffusion flame. It has, although it is not exactly diffusion, but we can say it is partially premixed or partially diffusion burning. Then we will move on to the physical features of laminar flame. As you must have seen in our previous lectures given by the Professor Marcus, he talked about what is the initiation of the flame. It started with a flame. The flame would have a velocity, it has a certain velocity, and if it has to move, it has to move in a particular directions. The propagation of charge and flame velocity should be same. That is the first criteria. Second thing, when the flame speed, when the flame moves, it is also moves with certain speed. It is followed by the charge which is moving behind it, and through this process, if and the charge which moves, uh, uh, it is in such a way that the flame speed and your charge speed, they may or may not be maybe or may not be different. So what one particular situation, at least the minimum condition is that the flame velocity should be same as the charge which is moving behind it, or unburned gases. In some cases flame travels at subsonic speed, some cases it travels at supersonic speed. So accordingly, that word laminar flame is termed as deflagration or detonation. Other kind of characteristics that is also required, the flame speed and thickness. This flame speed and thickness is controlled through this equivalence ratio, temperature and pressure, and of course the fuel type. And it also this flame speed detects the flame shape, stability, such as blow off or flashback. That means, as you told, if the flame has sufficient momentum, it can move towards the unburned gases and burn them. If it doesn't have, there are chances it can flow back. And if it has a more momentum, the flame will be moved most faster. So that way two situations can land up. One is blow off or flashback. So those things we will try to discuss. The other concept that we also need to explore, the flammability limit, ignition and extinction. So flammability limit, normally in ICE engine we say the equivalence ratio falls in certain range for initiation of the flame, or otherwise flame cannot be initiated. So during this period we can see a self-sustained flame, and that is the reason it is quantified through the flammability limit of any charge. Then ignition is the instantaneous phenomena that has to be there to create the to initiate the flame. Sometimes the flame has to be extinguished because it can create something effects, undesirable effects of explosion. So that thing we also require the concept of flame extinction. That means with that point of time we should somehow kill this flame speed to reduce its momentum. So all these parameters has to be looked into the discussion while talking about homogeneous combustion, uh, and we need to understand them through these characteristics of temperature profile. So here what we look at, we define a term what is called as flame speed, which is SL. We need to view this flame speed, flame, and by definition this flame is stationary relative to a laboratory frame in which reactants enters the flame with a flame propagation velocity SL. So flame speed and flame propagation velocity of the reactants or charge has to be same. So this is how we get that relation through this continuity equation, that conditions which is happens to be before unbound charge and after unbound charge. Now and this condition has to be satisfied for creating this flame. That means continuity equation that involves the any arbitrarily frontal area which involves density and the speed. Now coming back to its temperature profile, this is the generic trend how the flame propagates in a medium. Like here the flame is moving from right to left by carrying certain energy with heat, and with that energy it is trying to burn the unburnt fuel air charge. So if you look at this as a x, so we are looking at in this x axis we say it's axial distance, and we are trying to see how the changes that happens when the flame moves. So initially when there is no flame, it is the full of charge. When the flame happens, through this there are changes in the various factor. First, temperature, mole fraction. Mole fraction means once the charge gets consumed, its mole fraction comes down. So basically reactants are consumed, products are formed, and through this process there is a volumetric heat release. So the trend of these things is defined in this manner, that the mole fraction of the reactants comes down with axial distance. At one point of time it is almost zero. At that location we see this maximum heat release, and this is the typical plot that we normally encounter when you do experiments of heat release diagram, something we call as a P theta diagram in the IC engine terminology. And through this, initially the temperature is with respect to that of the condition which is at the reactant, slowly it increases maximum, and since this heat release diagram is impulsive in nature, so the temperature profile happens to be parabolic for corresponding to this impulsive nature of the heat release. So this is standard characteristics. We can say the temperature, although because temperature is rising slowly because of this heat, and what is peak heat release and maximum temperature location may be seen at some different location. And when you talk about some other term, like you can imagine this, for this thickness of this flame could be much lesser than 1 mm or maybe less, like and during this fast reaction we for a self-sustained flame, and we require some driving force. So driving force is nothing but the momentum the flame carries with it, and that comes from the heat that is released during the ignition process. If the heat is sufficient, then it drives the flame, If it is not sufficient, we cannot ensure a self-sustained zone. You cannot ensure a self-sustained flame. So because of this reason, the entire temperature profiles is characterized by two zones. One is preheat zone, other is reaction zone. During the preheat zone, you will find the reactants concentration or mole fraction in a higher to be higher. When reaction once the reaction is done, the charges gets consumed, temperature shoots up. That time those things we call this as a reaction zone. And all the reactions during this phase only, all reactions takes place through their element, either it in the form of elementary reactions and also in the form of global reactions. So the secondary zone extends to several millimeter means of atmospheric pressure, which means at this phase only your pressure rise is significant. Here another important aspect is that for hydrocarbon flames, the radicals CH that takes the dominance, and sometimes if depending on the conditions of stoichiometric, we get some kind of radiations either due to this carbon, and that is termed as blue green zone. And when OH radicals are formed, it gives to a reaction where carbon monoxide gives CO2. Now in our previous lecture we said that carbon always CO always needs to tend to mix oxygen to form CO2 if it gets a favorable environment, and through this formation it releases some radiation energy in the form of H nu, and this nu is basically talks about luminescence of the chemical luminescence of this reaction. Now when the flame becomes richer, soot formation comes, so it becomes a continuous black body radiation. This is a typical feature of a Bunsen burner flame that highlights and in order to see all those effects, we need to bring this concept of Bunsen burner flame, where what sir was explaining before, that we have a regulated knob which controls the air entering into it and fuel entering into it. By controlling the knob, we can generate two types of flame, laminar or diffusion flame. So typically for a Bunsen burner flame, it is characterized by two things. One is inner cone, other is outer cone. Inner cone is called as premixed flame and outer cone is diffusion flame. So this inner premixed flame is formed in the inner region with this, and that is mainly due to what air and fuel that enters with our control. But when this inner flame has a tendency, once it is framed, a tendency to mix with outside air. So that way when it mixes, it gets diffuses with outside air. So through this process we don't have any control of, there is no control of premixed concept. So it forms a outer cone, and that is called as diffusion flame. So this is the one characteristics that a Bunsen burner flame can give, where both premixed and diffusion flame. Now coming back to this inner flame cone, if you try to mathematically model the analysis, we can have one angle. Since it is a inner cone, we can define an angle alpha, which is called as local angle. The film sheet meets with a vertical plane, and there we have two velocity. One is onboard gas velocity. This can be decomposed along one axis of the cone and perpendicular to it, and this is with respect to the length of this cone, and other is normal to it. So for flame to be in a remain stationary, the flame speed must be equal to the speed of normal component of the velocity. So this condition has to get satisfied. So now other features of some laminar flame which replicates the similar phenomena, they are also seen in radiant burners. So this is with respect to engine, but this is with respect to burner applications. So actually when you see this in this particular applications, when you use this combustion as a household applications of designing the burners, we have different mechanisms in which the burners can be made, and they are mostly governed specifically through laminar flame, because we normally regulate the air and fuel where we have the charge and it takes the atmospheric air, and we see the flame on the top of the burner. That is what you see in conventional cooking stoves. So but there are variety of ways we can design these radiant burners that can be categorized in two parts. One is adiabatic burner, other is non-adiabatic flame burner. So this is something like those burners are designed to create flat flame. Here it is a planar flame, this is a flat flame. The design features involves boro structures as we discussed yesterday. There may be some screens, glass balls where fuel air mixture enters, and subsequently we generate the flame. Other structures is in this case we have similar to this glass ball, we have also the mechanism of improving the flame speed of the premixed charge, and the size of those holes essentially detects whether the charge will go in the forward directions or not. And these designs are very vital to ensure a sustained flame. So what we see in this flat flame on the surface, if it has to remain continuously as long as this fuel charge is there, it has to remain on the surface. These geometrical conditions as well as the fuel condition has to be ensured simultaneously. So for laminar flame, the maintaining a sustained laminar flame is really challenge when you are looking at particularly for burner applications. I also mentioned that when the flame sits on the surface, that means always this charge, always the charge should have sufficient momentum so that flame remains on the burner, and if it doesn't have, it tries to move down. So always one condition is, that means there are two possibilities. The flame can sit on the surface, that is the most ideal case. The flame may blow up. Blow up means it has sufficient momentum. It doesn't sit on the surface, rather at some distance from this surface. Other situation could be the flame can propagate back. Propagate back means if that condition is not maintained, onboard charge, gas and flame velocity, when it goes back, so it can directly come to this fuel air charge, that means flame is moving back. So this kind of situation creates the explosion. So we call this as a flashback. To ensure this flashback not to happen, we require some kind of mechanism uh, in the form of flame arrestor, or this kind of design will help you whether we can arrest which ensures that, for example, as we are discussing the last class, the holes are such that it can only allow the forward charge. It cannot allow the flame to enter it, and once the flame tries to enter it, it cannot sustain by itself because the bore diameters or sizes are not favorable for it. So that way the flame is killed at this stage itself. So at any kind of things for explosion needs to be avoided, we require the flashbacks not to happen. This is exactly over the years our cooking gas cylinders are designed. There, although there are accidents are happening, but not due to its design, but due to something else, negligence. But designs are such that either at any circumstances, by mistake, if you it is charge is on, if your regulator is not functioning properly, uh, if it is regulator is functioning properly, at no circumstances the flame can uh, propagate back to the cylinder. But if those defects are there, then normally the accidents happens. So if at all, and some cases explosions are required, some cases explosions are not desirable. So explosions, something like when you think about controlled explosion, it can give a short duration thrust into the system. So these are some critical features that we looked into while talking about laminar flame. Then I'll try to move the factors that controls the laminar velocity. Two major factors are there, temperature and pressure, because these two parameters essentially rises. First thing is that the flame speed is strong dependence on temperature, and also because that is mainly for hydrocarbons, and their activation energy falls in this range 1.67 into 10 to the power joule 8 joule per kilomole, and this increase in the temperatures leads to dissociation. And one simple thing we can correlate mathematically, or correlations that can be developed, is that in the domain of 300 to 600 Kelvin, the increase in the flame speed, the increase in the temperature from 300 to 600 results in the flame speed increase by a factor of 4.3. So flame speed increases with temperature. So the dependence of flame speed with temperature is correlated by this expression. Dependence of flame speed with respect to pressure is correlated by this expression, where we talk about this flame thickness, which we talk about 1 mm or less, is delta is equal to twice alpha by SL, and alpha is nothing but your heat transfer parameter, thermal diffusivity, K by rho Cp. Other part that the flame speed depends is the equivalence ratio and flame type. Equivalence ratio creates a major role, because depending, when you say that if you refer one typical diagram which you have discussed earlier, the role of equivalence ratio in the form of heat release or adiabatic flame temperature, we see that at equivalence ratio of close to 1, or at this case at least 1.05, heat release is maximum. This is normally what you see. uh, and for all hydrocarbon fuels this number is fixed. That's what we say adiabatic flame temperature when it approaches. It is true for all kinds of hydrocarbon flames, but these numbers will be different if you are using hydrogen. Why it is say? Because hydrogen's flame speed is much faster than any kind of hydrocarbon flame, and here it is the case of propane. So it's a propane air mixture. Why it is so? Because if you if you see here, this alpha plays a critical role. Thermal diffusivity and mass diffusivity of hydrogen is many times higher than the hydrocarbon fuel. So when we have this, when you have hydrogen into the system, since the flame speed is higher, the reaction kinetics is much faster. So that is the reason uh, uh, we say that in the presence of hydrogen reaction kinetics is faster, and this also helps that non-formation, because when you have a rapid reaction, the relative slower reaction which is absent when there is a presence of hydrogen, and in fact it also acts as a kind of a catalyst for a favorable case situation. Another relation which it is more versatile, but here if you look at here these cases, this flame spill because when this concept was evolved, people tried to see dependence only on pressure or dependence only on temperature through this correlation, but simultaneous control of pressure and temperature is not there. So that way another generic formula was formed for developing a laminar flame speed, and it is based on the correlations which are developed with reference to a reference conditions and with the conditions at which we are looking at, or any arbitrary conditions. The arbitrary condition is nothing but temperature of unbound charge and pressure at that point. And but when you look at this flame speed at some reference pressure and temperatures, so this way we can calibrate a systems with certain pressure and temperature as a reference conditions, and it will give you a corresponding laminar velocity or burning speed at that reference conditions. So this is framed in this manner: ratio of temperatures, pressures. Additionally, it also looks after any kind of diluent present in the phase charge. So that means if the mixture is not perfect in the form of fuel and air, if there is some additional components present, and if you are able to quantify that mass fraction, then this can be also linked to laminar fluid calculations, and this particular relations always valids when temperature is higher than 350 Kelvin. And this reference condition is calculated by some parameters. These parameters are specific to fuel air charge. This can be we can get from data book, and phi and all these are the terms that constants, phi, b1, b2, they depend on that. So all the numbers are known. So basically what you all know the reference conditions, and if you are able to know what temperature or pressure you need to find out, then we can find out this value. In some cases, if this Y mass fraction of any other undesirable products is absent, so this factor stops with this calculation stops at this point. So this becomes 1. This term becomes 0, and It has no effect on the laminar speed calculations. This is most standard relations that are being followed as long as your temperature is higher than 350 Kelvin. So I have explained all these things. Now with this we say that there are some laminar speed calculation is there, we will be able to get, and once the flame moves, at least through this correlation we can find what is the velocity. Now I am just trying to give some repetitive things which you will find from classical textbooks of any ice engines, just to correlate that uh, what happens, because those point of time we normally don't talk about the details of flame, but once we have flame generated in the engine, and we say there is a rise in the pressure as well as temperature. Now if the rise in pressure and temperature are not desired as per this user, what is the going to be end effect? So this is the question we are going to normally study for homogeneous air fuel mixture, and if the combustion is not complete, what is going to happen? So one thing here is that the role of flame is to kill all the fresh charge, because it has a uh, characteristic of rise in the pressure. That rise in the pressure we subsequently ignites the next layer of fresh charge. So in the ice engine, initially we have a, if you can see, this is your engine domain. This is just to give a schematic. You have engine domain, spark is initiates a flame, and that engine domain is designed into 4 zones, and it can be n number of zones, just to explain how the flame moves at when it is at one instant of time. So initially zone 1, zone 2 or zone 3 are of same pressure and temperature. Once you create a spark, in the zone 1 the pressure temperature rise shoots up, because the flame generates and it tries to propagate. At one instant of time, zone 1 is now full of combustion products, but zone 2, 3, 4 are still unburned charge. So as the flame moves, it tries to spreads the rise in the pressure and temperatures. Slowly it is moving in their directions. So this one in the ice engine term we call this as a flame front, which propagates into the in the cylinder, and this propagates with a flame velocity. This is nothing but our SL, and this flame propagation is caused by heat transfer and diffusion burning of the fuel molecules from the adjacent layer of burnt mixture. Where is this? Where it gets the charge? For example, it burns this layer, it gets the momentum from this, from this previous charge. Now it went to this another kind. This momentum is further raised. So that way, that way it gets energy in the form of heat by adjacent layer of unburnt gas mixture. This keeps and this for a homogeneous mixture, we typically have that flame velocity is of the order of 0.4 meter per second. This is just to quantify some kind of number, and this is observed in this equivalence ratio of this 1.1 to 1.2. Now if the equivalence ratio is not favorable, means from the next layer of charge, if the flame does not receive sufficient energy, it assumes that it gets cooled. Subsequently, when it moves, your heat is continuously rising. If it is not rising, means the flame is getting cooled, because unburnt, because the flame doesn't have sufficient, the charge doesn't have sufficient strength. So that way equivalence ratio has to be maintained in with a reach value. Now three kind of broad regions that we get in this combustion process: ignition, flame development, and flame ignition and flame development, flame propagation, and flame termination. Why such things are required here? That if you look at this figure again, the flame propagates. Its main role is it has to kill all the fresh charges. And while killing all the fresh charges, it should not kill at any intermediate liquations. It should kill all the charges when it starts its journey from its spark plug location till the end. So all the charges has to be killed, or fresh charges has to be consumed only when the flame reaches at the location 4. That is the most ideal situation. And through this process, it is viewed that initially you start with ignition, then flame development, flame propagations with certain speed, and the flame termination. Flame terminates at this. So that way we say at one instant when the flame is not there, it is only a fresh charge, and when the flame completes its role, it is the full of combustion products that has to come back. This is the most ideal situation. Now if it doesn't happen, then it gives some kind of undesirable phenomena, and in a qualitative way we call as a knock, which quantitatively way it's a undesirable pressure pulses, which means that pressure rise has happened, still the flame is there. Pressure rise has happened, but still the flame is sitting in the chamber. So those things we see in the pressure traces or temperature traces when you actually take it. So this is the most classical diagram that you see in the form of P theta diagram, pressure and crank angle, where we start our ignition. Maximum pressure is somewhere seen when phi is equal to 1.05. Sorry, this is phi is equal to 1.05. At that point, we ensure that we have adiabatic flame temperature, pressure is sufficient here, and ignition. This is the flame propagation zone, and finally, at this point, when we are towards the end location, the flame started terminating. And typically during ignition phase and development, it is done through a spark plug. With that spark plug has some it's nothing but a electrode, and it just a point to be noted here that we create a voltage potential about 25 to 40 kilovolt that turns out to be maximum current to be 200 ampere, but it is not that significant because it lasts for 10 to the power minus second. And during this time the temperature shoots up to a very large value, because during the lasting period of the combustions. But however, you really do not have to bother so much temperature, because whatever the situation that happens in a nanoseconds level. This is a typical curve that we get in terms of voltage and current when you do in the spark plug. But what we require through the spark plug is very small quantity of energy in the range of 0.2 megajoules. Now these are the some standard things that when during a flame propagation period, the fuel air mixture is consumed about 80 to 90%. So initially that's a very small amount. During flame propagation period, the fuel air mixture is consumed about 80 to 90%. So this part I have already explained. As the flame plant moves in the combustion chamber, what it causes. Either it can cause knocking, or uh, if it doesn't reach at this point. So this particular experiment shows that when the suppose your flame front is at some location, and it has not reached this because undesirable mapping of pressure, temperature and charge. So knock can happen only at this location. Knocking cannot happen because these are already the combustion products have already formed. So this is another curve that shows that what is the mass of the charge that gets burnt with respect to percentage of volume which is burnt. Here also the same things which I have explained, they are written in this manner. What we look at is this particular figure, what happens during a knock. So if during the flame propagation period knock can happen, so how? Because for a normal combustion the pressure time trend is smooth. Now when there is a slight knock, because the highest pressure is felt at this location where equivalence ratio is close to 1. At that point of time, if we see pressure pulses in erratic manner, that is a tendency of knock or higher pressure pulses, and with heavy knock these oscillations becomes more significant. Now while at which location it can happen? It can happen towards the end, because the flame has not terminated, the pressure has increased, so it tries to give some pressure onto this wall of this cylinder. That is trend is reflected in the form of pressure traces. These are some of the things that it is classical stuffs, which is the concept of flame propagation zone. There is another term called as burn angle, which is the parameter that quantifies that during certain time the charge gets consumed. That is the period we call this as a burn angle. Then final case, that the flame has to be terminated. This has to be terminated when the flame reaches here, and during this phase last 5% of the fuel air charge gets consumed. So these are the some of the thing. There are some situations we can see there is a self ignition. In fact, the self ignition is one of the characteristics why that is a pressure rise, because the flame has not reached, but the charge which happens to be here and which happens to be burned by the flame, what it does, it self ignites on its own. Because of this reason, these pressure pulses shoots up, and these pressure pulses are detected through a phenomena called as knock. Okay, so this is all about this lecture that talks about the concept of laminar flame. How that laminar flame concept we are doing in the case of we are viewing in a homogeneous mixture of burning of fuel and air in an IC engine, spark ignition engines. So this slides also talks about introduces some kind of solving problems for laminar flame. And first problem is something like correlates between the onboard charge and flame velocity. That through that relations one can have to find out for a particular case methane air flame what should be the flame velocity. And this talks about the horizontal and vertical distance through this because if you view this flame in a plane, we have horizontal distance and vertical distance, we have angle. So during that phase, how the flame speeds is evaluated. The another problem that talks about the that will give you about the importance of this particular correlation, general correlations to calculate the flame speed from its at again any arbitrary given situation with respect to a reference conditions. So this is all about this lecture. I will conclude here, and the next lecture will be given by Professor Marcus. Thank you for your attention.